Okay, good morning. We are ready to start. Just a quick confirmation. You are able to see the shared screen? Anyone?
Yes, sir.
Great, great. Thank you. Thank you very much. Okay, so we have talked about some examples of random processes or stochastic processes, and today we are going to talk about a very special type of a random process. So next 2-3 lectures, maybe 4 lectures, will be devoted to what we call Markov chains. Markov chains. So Markov chains is an example of a random process. We will specifically talk about discrete time Markov chains, or DTMC, or continuous time Markov chain, CTMC. Both very important, used to model a lot of physical processes which are concerned about moving from one state to another state, and we will explain what we mean by a state. So let me just first focus on the discrete time Markov chain. By the way, both of these discrete time and continuous time Markov chains, they have discrete alphabet. Which means, remember, we have been talking about the random processes, and the random processes has time here along the horizontal axis, and the value of the random process is here. And the value of the random process can be discrete or continuous. So vertical axis here, we are restricting the vertical axis to be discrete. So Poisson process tha hamare paas, it was a discrete alphabet random process. कि एक given time के अंदर आपके पास कितनी arrivals होती हैं, वो जो कितनी arrivals हैं, that was a count. So discrete number there. So we have a discrete alphabet both for the case of discrete time Markov chain and for the continuous time Markov chain. The only difference is कि horizontal axis जो है DTMC के case में it would be discrete, CTMC के case में it will be continuous. That's the only difference. Vertical axis जो है इसमें, which is the value that the random process is giving you, that will always be discrete. Now recall what was the random process? Random process was कि you have to look at the random process at a specific instant of time. If you look at this time, okay, what you are going to look at is a random variable here. What about here? If you look at this instant of time, you will see another random variable drawn from the same experiment. जो एक random experiment आपने किया था, sample space से कुछ outcomes आ गई थी, वो एक ही दफा करना है शुरू में, वो बार बार नहीं करना, हर दफा random variable generate करने के लिए वो experiment नहीं करना. You just need to do that random experiment once at the beginning, at t is equal to minus infinity or t is equal to 0, wherever is your starting time. Okay. Once you perform the random experiment, now you are done. Okay. And then at every instant of time, you will see one mapping function from the outcome onto the real number. तो outcome आपकी जो है वो black भी हो सकती है, outcome आपकी red भी हो सकती है, और red will map to the red value, and the outcome can also be green, which will map to the green value. So if your experiment at the beginning of the time resulted in an outcome which was red, so at this instant of time you will see the red value. At this instant of time you will see this other red value. May not be the same as the red value at the first instant. Okay. So सो t इज इक्वल टू t1 के ऊपर आपको रेड नजर आएगा, t इज इक्वल टू t2 के ऊपर भी रेड ही नजर आएगा, बिकॉज आपने जो एक्सपेरिमेंट किया था उसकी आउटकम ही रेड आई थी। तो ये अब हमेशा हमेशा के लिए फिक्स हो गया कि आपको रेड ही नजर आएगा। लेकिन डिफरेंट टाइम्स के ऊपर वो रेड ऊपर आता है नीचे आता है, क्या वैल्यू लेते हैं, that is something which can change, that is something which can change. So for example, at t is equal to t3 for example, so if I have a time t3 here, t3 के ऊपर what value the red will take we don't know, ये आपके पास तीन choices होंगी, so one green, maybe one red, and then one black. So if your random experiment resulted in red outcome, so at t is equal to t1, the random process will take the value this red. At t is equal to t2, the same random process will take this value. At t is equal to t3, the same random process will take this value, जो भी ये vertical axis के ऊपर reflect होती है. So at every instant of time, we have one random variable. Now, discrete time Markov chain, इसके अंदर दो चीजें, एक तो मार्कov चेन है और एक डिस्क्रीट टाइम है. सो सबसे पहले हम टाइम को डिस्क्रीट कर देते हैं. सो लेट्स मेक दीज टाइम इंस्टेंट्स डिस्क्रीट. सो इनको मैं इंडेक्स कर देता हूं एट सम नंबर्स 1 2 3 4 5, इस तरह से हम इनको नंबर कर देते हैं. ओके, एंड रियली वी डोंट नो what is the actual time between 1 and 2. What is the actual time between 1 and 2? It could be 1 second, it could be 1 minute, it could be 1 solar year. ठीक है, हमें कुछ पता नहीं है. The only thing we know is that the time is discrete. I am going to only look at these random variables at t is equal to t1, t is equal to t2, t is equal to t3. Nothing in between. Nothing in between. Okay, so ये आपके पास discrete time random process ऐसे ही होता था. Discrete time as random process ऐसे ही होता था. So this random process is discrete time as well as discrete alphabet. If I let the time to be continuous, this will become a continuous time random process with still discrete alphabet. Poisson process was an example of a discrete alphabet continuous time random process. Discrete time Markov chain, time is discrete and these values are also discrete. Now, if anyone recalls the Wiener process was a discrete, we saw a discrete time version of a Wiener process. There was a real Wiener process जो continuous time था, but we saw the discrete time version of the Wiener process. So discrete time version of the Wiener process, हर discrete time के ऊपर n is equal to 1 2 3 4 values के ऊपर आप observe करेंगे. What you will observe would be a normal random variable which has continuum of values. So that means के Wiener process के अंदर जो alphabet है वो continuous होता है. For Markov chains, the alphabet is always going to be discrete. But in addition to that, ये ऐसे ही just discrete नहीं होगा. हमने ये करने के जितनी भी discrete values हैं, we will signify them using some states. So this is your stochastic process, which is time indexed sequence of these random variables. उसको अभी discrete time Markov chain के लिए time को अभी हम discrete रखते हैं. For discrete time Markov chain. Okay? और इन values को हम ये करते हैं कि each of these values मैं इनको states कह देता हूं. And these values will take a finite number of values. हैं ये आपके पास. So xn time index denoted by n, and xn उसको मैं कहता हूं कि this is the state at time t is equal to n. At time n. So xn can take many different values from this state. So you have n here, which is the time, and it's going from 1, 2, 3, 0, 1, 2, 3, 4, dot, dot, dot. Now, I am going to draw one sample function. एक मैं sample function draw करने लगा हूं, और वो sample function ऐसे हो सकता है कि first you have this state, and then maybe you have this state, and then maybe you have this state. So you might have noticed that I am using the word state, but it's really the values. It's really the values. ये एक value आ गई, ये एक value आ गई, और ये एक value आ गई. So maybe our entire random process is limited to these three values. Discrete में जरूरी तो नहीं है 3 हो, 4 भी हो सकती हैं, 5 भी हो सकती हैं. Vertical axis is discrete, but it doesn't mean कि discrete जो है वो 3 ही हो, वो 5, 6, 8, 10. It is countable. When I say discrete, it is countable, and this can actually be countably infinite. Could be countably infinite. There are Markov chains which will have these infinite states. So I represent these states कि इन values को मैं कहता हूं कि ये एक state है, ये एक और state है, ये एक और state है. And then maybe at t is equal to 4, 5, 6, I choose one of these states. So let's say कि 4 पे ये state हो जाती है, 5 पे ये state हो जाती है, 6 पे फिर ये state हो जाती है, 7 पे ये state हो जाती है. And these states are just chosen like that. This is one sample function. So see that at every instant of time, if I look at n is equal to 1, I had 3 possibilities. एक जो एक क्रॉस लगा दिया है, एक ये possibility थी और एक ये possibility थी. So this entire random process can have only these 3 values. उन 3 values को जो है वो मैं स्टेट कह देता हूं, ठीक है. और इसके सेट को मैं स्टेट स्पेस कह देता हूं, स्टेट स्पेस. सो आई कैन ओनली हैव 3. इस जगह पे हमारे पास सिर्फ वो जो 3 वैल्यूज रैंडम वेरिएबल दे सकता था, जिसमें से मैंने एक सैंपल फंक्शन ड्रॉ किया है. I have drawn only one sample function. I can draw other sample functions as well. Okay, I can draw other sample functions as well. So state space is typically, आप स्टेट्स को कुछ भी नाम दे सकते हैं, स्टेट ए, स्टेट बी, स्टेट सी, कुछ भी नाम दे सकते हैं, बट typically numbered, okay, can give non-numeric names to states, but typically they are numbered. Typically इसको जो ना numeric ही रखते हैं. Okay? If you have finite number of states, this implies that we have a finite state discrete time Markov chain. Okay? And you can also have countable but infinite states. एक क्या एग्जांपल होगी उसकी? स्टेट 1, 2, 3, 4, 5, 6 all the way up to infinity. It is countable but it is infinite. Okay, so countably infinite states, this is called an infinite state or just infinite DTMC. Still discrete time. It is still discrete time, and still it is a Markov chain. The alphabet will still be discrete, will always be discrete. So alphabet always discrete and actually manifests as state in the state space. वो जो state space है उसके अंदर से एक state कोई हो. So हर टाइम के ऊपर, हर discrete टाइम के ऊपर, you are moving from one state to another state. Okay. A property of the discrete time Markov chain, and also for the continuous time Markov chain, is that it is a Markov process. It is a Markov process. Markov chain is a Markov process. Markov process. What that means is, okay, given the present, future is independent of the past. Future is independent of the past. Okay. Markov property is satisfied by the Markov processes. Okay. So I will give you an example. Finite state discrete time Markov chain example, and you will appreciate okay, how simple is this? How simple is this? Okay. So let's look at the daily weather. Daily weather. It could be rain, it could be a rainy weather or sunny weather. Rain or sun. हर डे को हम क्लासिफाई कर देते हैं, ये रेनी है या सनी है, ठीक है, दरमियान की कोई चीज नहीं रखते, या रेनी क्लासिफाई कर देंगे या सनी क्लासिफाई कर देंगे. So on every day you can have either rainy weather or sunny weather, rainy weather or sunny weather as. These are two states. Okay. So states जो हैं हमारे पास वो हैं वो R और S. This is your state space. ये सिर्फ दो ही पॉसिबिलिटीज हो सकती हैं हर दिन यही दो पॉसिबिलिटीज हो सकती हैं. So let's say I'm going to draw a sample function here. So let's say you have time here and at n is equal to 0, 1, 2, 3. 0 से शुरू कर लें, 1 से शुरू कर लें, up to you, totally up to you. Okay. So maybe you have R on this day and then sun on this day, and then R on this day and sun on this day, and then sun on day 4, and maybe another sun on day 5, and so on and so forth. This is one sample function. We, instead of calling it a sample function, चूंकि ये मार्कov चेन है जिसमें हमने इनको स्टेट बना दिया है, तो हम इनको कह देते हैं कि दिस इज ए स्टेट ट्रांजिशन फंक्शन. Okay. So I will give you what we call a probability transition from one state to another. So you transition from one state to another state. ये transition कैसे होती है? So we call this, let's say, the probability of transitioning from rain to sun or sun to rain. So Pij is the probability you transition from state I to state J. Pij is the probability you transition from state I to state J. ये rain वाली example के लिए, rain और sun वाली example के लिए, I'm going to explain what those probabilities are, and these are called the transition probabilities. So let's say, what are the possibilities here? Maybe you have rain and you have sun on one day, and on the next day, next day, so this is today, and this is tomorrow. This is today or this is tomorrow, or this is on day 10 and tomorrow is day 11, day 10 or day 11, or day 15 and day 16. So 2 consecutive days पे बना रहे हैं. So पहले दिन आपके पास rain हो सकती है, and then you can also have rain, and there is a probability that if you have rain today, what is the probability you will have rain tomorrow? So this probability is alpha, and the probability would be 1 minus alpha, that if you have rain today, then you will have sun tomorrow. Okay. Similarly, beta and 1 minus beta. Okay. So probability of rain on day n plus 1, given that you have rain on day n is equal to alpha. So given that you have rain on day n, what is the probability you will have the rain on the next day is alpha. So similarly, probability of sun on day n plus 1, given that you have rain on day n. So again, rain on day n, if this is given to you, there are only two possibilities you can have something on the next day. Ya rain ho sakti hai ya sun ho sakta hai. If the probability of the rain is alpha, then this must be 1 minus alpha. Must be 1 minus alpha. Why? क्योंकि दो ही पॉसिबिलिटीज हैं आपके पास. आपको मैंने बता दिया है कि आज रेन हुई है, आज रेन हुई है. अब बताएं कि कल क्या होगा. कल या रेन होगी या सन होगा. If the probability of the rain tomorrow is alpha, then probability of sun tomorrow is 1 minus alpha. Similarly, if the probability of rain on day n plus 1, given you have sun on day n, आज आपके पास sun आया है, आज आपके पास sun आया है. So today you have sun. What is the probability you will have rain tomorrow? It's beta. And similarly, the probability of sun on day n plus 1, given you had sun on day n, is 1 minus beta. 1 minus beta. So what we do is that we write these guys, this transition probabilities, in a matrix form, and this matrix is called probability transition matrix. You will see that putting it in the matrix form is very, very useful. Very, very useful. Okay. So I'm going to define Pij as probability that xn plus 1 is equal to j. So you are going from state I to state j. एक step आपने लेना है, और you are moving from state I to state j, given that xn is equal to I. When I and j, they are the element of the state space. I और j ये दो states हैं पूरी state space के अंदर से, उसके बाहर से कुछ नहीं हो सकता. And this is true for all n. This is true for all n. किसी भी n के लिए ये true होगा, और ये change नहीं होना चाहिए. ये change नहीं होना चाहिए. Otherwise, you will have what we call a non-stationary probability transition matrix. Okay? ये probabilities हमारे पास हमेशा constant रहेंगी. So अगर मैंने आपको बता दिया कि given today, what is the probability, given the weather today, what is the probability of rain tomorrow? ठीक है? The same probability will apply if I tell you कि day 13 के ऊपर जो weather, if that weather is given to you, what is the probability of rain on day 14? Should be exactly the same. Should be exactly the same. Okay. Any questions so far? Great. So now we have this probability transition matrix. Probability transition matrix. I will draw the Markov chain as well. So let's say you have example. Let's say you have a Markov chain with two states. Markov chain, discrete time Markov chain with two states. और ये आपके पास states हैं 1 and 2. So आपकी जो state space है वो क्या हो गई? State space is 1, 2. मैं A और B भी कह सकता था, X और Y भी कह सकता था. I'm just calling them two states, state 1 and state 2. So this is state 1. Okay. This is state 1 and this is state 2. This is state 2. and at each time step you move from one state to another. या ये भी हो सकता है कि आप उसी स्टेट पे खड़े हैं, ठीक है, जैसे हमने ऊपर एग्जांपल दी है कि या रेन से सन पे चले जाएंगे, रेन से सन पे चले जाएंगे, या सन से रेन पे आ जाएंगे, ठीक है, या रेन से सन पे चले जाएंगे. दिस प्रोबेबिलिटी शुड बी द सेम एज दिस प्रोबेबिलिटी. लेकिन ऐसा भी हो सकता है आप सन से सन पे ही रहें, सन से सन पे ही रहें. So you can actually move from state 1 to state 2, state 1 to state 2 with certain probability. And what is that probability? This is P12, P12. Okay. And similarly, you have this probability P21. You are moving from state 2 to state 1. ये कुछ वैल्यू हो सकती है. There might be a possibility that you start from state 2 and you stay in state 2. So this is the probability P22. कि एक स्टेप में, एक टाइम स्टेप में you go from n is equal to 17 to 18, टाइम 17 to 18 पे आप गए हैं और 2 से 2 पे रहे हैं. So that's the probability P22. And similarly, this is the probability. Oops. This is the probability P11. P11. Very, very easy. अभी तक कुछ हमने किया भी नहीं है, नई चीज कोई कुछ भी नहीं आई है, ठीक है. So let me give these guys some numbers. So let's say I give this guy a number 1/2. इसको दे देते हैं, और if this is 1/2, then this must be 1/2. Why? Answers in the chat window. If P11 is 1/2, then P12 must be equal to 1/2. Why? कोई आंसर देगा? Only two possibility. तो दोनों को ऐड, स्टेट 1 से आप या स्टेट 1 में खड़े रहेंगे या स्टेट 2 में चले जाएंगे, इसके अलावा तो और कुछ नहीं हो सकता. So those probabilities must add together. Similarly, I can pick this example कि this guy is 1/3. So P21 ये कितना होना चाहिए? P21 कितना होना चाहिए? Answer in the chat window. P21. It should be 2/3. Thank you, Rafa. Should be equal to 2/3. 2/3. So I can draw the probability transition matrix. Probability transition matrix is transition matrix of this is going to be P11, which is 1/2, and P12, which is also 1/2. This is 2/3. This is 1/3. This is our probability transition matrix. Probability transition matrix. And we understand that summation k is equal to 1 to whatever number k is the element of S. ऐसे कर देते हैं. Pik should be equal to 1. Should be equal to 1. क्यों? क्योंकि आपके पास वही पॉसिबिलिटीज हैं, k पॉसिबिलिटीज हैं, और k पॉसिबिलिटीज ही हैं, उन सब की प्रोबेबिलिटी आपके पास होनी चाहिए. So today you are at state I. Today you are at state I. Tomorrow or one day from whatever, अगर today आपने नहीं select करना, tomorrow you must be in one of the k states. Should be in one of the possible states, उसके अलावा कहीं नहीं हो सकते from the state space. स्टेट स्पेस के अलावा और किसी जगह नहीं हो सकते. So I'll give you another example. एक और example देते हैं. Another example. So let's say you are given a probability transition matrix, and the probability transition matrix is 1 by 4, 1 by 2, 1 by 4. I'm going to ask if this is a probability transition matrix. 2 over 3, 1 by 2, 0, 1 over 3. Is this a probability transition matrix? Yes or no? Answers in the chat window. This is no. Why? Because ये रोज जो हैं ये एड अप होके 1 होनी चाहिए. ये रोज एड अप होके 1 होनी चाहिए. पहले में होती हैं, दूसरे में होती हैं, तीसरे में नहीं हो रही. So I'm going to change this. I'm going to change this and make it 1 over 2 here. 1 over 2. Is this a probability transition matrix now? Yes or no? Yes or no? Answers in the chat window, please. Yes, this is a probability transition matrix. I can draw the state diagram for that. How many states? How many states? Answers in the chat window. How many states? 3 states. क्या मैं बता सकता हूँ उन स्टेट्स के नाम क्या हैं? A, B, C हैं या 1, 2, 3 हैं या 5, 6, 7? Can I tell that? No, it doesn't matter. It doesn't matter. All I know is that there are 3 states. I can call them any states. Any states. I will just go ahead and call them states 1, 2, and 3. Although it is entirely arbitrary. Entirely arbitrary. So I have state 1. I have state 1, state 2, and state 3. So I'm going to draw this state diagram. This state diagram here. This is a state transition diagram. State transition diagram. So ये देखें 1 से 1 पे ही रहे वो next time के अंदर. So you started with 1 and in the next instant of time you stay at 1 with probability 1 over 4. Okay. So you start with 1 and move on to state number 2 with probability 1 over 2 and move on to state 3 with probability 1 over 4. That makes sense? Yeah. So I'm going to pick the second row now. Going to pick the second row now in maybe red color. Okay. Second row, and you move on to the first state with probability 1 over 3. Second row, and you stay with the same with probability 0. So there is no self loop here. No self loop here. So if you are in state 2, you must move out of state 2 in the next state. तो ये state 2 से ये नहीं हो सकता कि एक टाइम पे अगर state 2 में आ गए, next instant के ऊपर, next time index के ऊपर, you have to move out of state 2. And how do you move out of state 2? 1 by 3 probability, either you move to state 1, and 2 by 3 probability, you move to state 3. Make sense? ये देखें ये वाला self state का state जो है, ये हमारे पास नहीं है. Why it is not there? Because उसने बस 2 में से निकलना ही निकलना है. उसने 2 से निकलना ही निकलना है. Now, from state 3, you can go to state 1 with probability 1 over 2 and stay in state 3 with probability 1 over 2. Okay. So this may be in a different color. I should do it in a different color. Green may, with 1 over 2 probability you are here, and with 1 over 2 probability you stay here. There is no way to move from state 3 to state 2. डायरेक्टली आप नहीं जा सकते, फिर पहले 1 पे चले जाएं, फिर बाद में 2 पे चले जाएंगे, हर टाइम की इंस्टेंट के ऊपर आप चेंज करते जाएंगे. सो दिस डिस्क्राइब्स द मार्क ऑफ चेन. This describes the Markov chain governed by this probability transition matrix. इस probability transition matrix के साथ ये वाली आपके पास Markov chain है. So कुछ इसी Markov chain के ऊपर कुछ एग्जांपल ले लेते हैं. So first example, what is the probability x4 is equal to 2 given x3 is equal to 2? Answers in the chat window. Answers in the chat window. एक टाइम x3 का मतलब है कि 1 2 3 4 5 you have n here. So x3 का मतलब है टाइम 3 के ऊपर आप देख रहे हैं, x4 का मतलब है टाइम 4 के ऊपर देख रहे हैं. So 3 से आपने 4 पे जाना है. So what is the probability you will go from state 2, this is state 2 to state 2. टाइम 3 के ऊपर you are at state 2 and टाइम 4 के ऊपर you move to state 2. ऐसा हो नहीं सकता. Why? Because 2 जो है वहां से आपको बाहर निकलना ही निकलना है. या आप स्टेट 1 में चले जाएंगे 1/3 प्रोबेबिलिटी के साथ, या आप स्टेट 3 में चले जाएंगे 2/3 प्रोबेबिलिटी के साथ. ठीक है. सो दिस प्रोबेबिलिटी इज 0. What is the probability x6 is equal to 1 given x5 is equal to 2? Answers in the chat window. अभी ये जल्दी से बताना. Answers in the chat window. So this is 1/3. Everyone agrees with that? That is great. Okay. Part C. Given x naught is 1, so you are in state 1 at time 0. Let's say 0 से हमने start कर दिया. At time 0. Okay. Given x naught is equal to 1. What is the probability x1 is equal to 3? What is this probability? Is 1/4. This is good. So somebody has asked, can it be the case that some state has probability 1 for self loop, then there will be no transition out of that state? That is correct. And that state is called an absorption state. इसका क्या मतलब है? इसका मतलब आपका रैंडम प्रोसेस बस उस स्टेट में फंस जाएगा, फिर वहां से वो निकल नहीं सकता. ठीक है. We'll give you an example of that as well. So this actually is not probability x1 is equal to 3. इसको ऐसे लिखेंगे नहीं. This is written as probability x1 is equal to 3 given x naught is equal to 1. So this is 1/4. So I'm going to ask another question. If probability of x naught is equal to 1 is equal to 1/3, there is a 1/3 chance you started the process at t is equal to 0, at n is equal to 0. तो 1/3 chance था कि वो इधर होगा, 1/3 chance था कि state 2 में होगा, 1/3 chance था कि you will start with state 3. ठीक है. So if you started with state 1 with probability 1/3, if you started with state 1 with probability 1/3, what is the probability that x naught is equal to 1 and x1 is equal to 2? What is the probability x naught is equal to 1 and x1 is equal to 2? So यहाँ पे हम multiplication rule लगाएंगे. Probability of A and B is equal to probability of A into probability of B given A. Multiplication rule. Okay? So this would be equal to probability x naught is equal to 1 into probability of x2 is x1 is equal to 2 given x naught is equal to 1. Okay. What is this probability? पहले वाले का बताएंगे फिर दूसरे वाले का. What is the probability x naught is equal to 1? It's just given to you. It's 1/3 multiplied by what is the probability? What is the probability? x1 is equal to 2 given x naught is equal to 1. What is the probability x1 is equal to 2 given x naught is equal to 1 is 1/2. Is 1/2. तो ये आपके पास 1/6 आ गया. एक और पार्ट करते हैं इसमें. Given probability of x2 is equal to 3, find the probability x2 is equal to 3, x3 is equal to 1 and x4 is equal to 1, x5 is equal to 2. ये probability find out करनी है. Who will answer this question? ये मैंने state transition diagram भी ऊपर रख दी है screen पे. Who will answer this question? इसका आंसर निकालें अपने पास. This is, let's say, it's 1/3. इसको लिख सकते हैं, x2 is equal to 3 into probability of x3 is equal to 1 given x2 is equal to 3 into probability of x4 is equal to 1 given x3 is equal to 1 into the probability x5 is equal to 2 given x4 is equal to 1. कौन ये आंसर कर सकता है? Who can answer this question? So देखें सारी probabilities आपको दी हुई, सब probabilities आपको दी हुई हैं. This is the probability of x2 is equal to 3. This is given to you as 1/3 into x3 is equal to 1 given x2 is equal to 3. So ये आपके पास 3 है और x3 is equal to 1. This is the probability 1/2. And then x4 is equal to 1 given x3 is equal to 1. So ये 1 से 1 में रहने की probability है. So this is equal to 1/4 into probability x5 is equal to 2 given x4 is equal to 1. x4 is equal to 1, x5 is equal to 2 is also 1/2. Also 1/2. So जो भी आंसर निकलता है. If I ask you this question, given probability x2 is equal to 3 is equal to 1/5. Okay. Find the probability x2 is equal to 3, x3 is equal to 2. x3 is equal to 2. कौन आंसर करेगा ये? So this is the probability x2 is equal to 3 into the probability x3 is equal to 2 given x2 is equal to 3. What is the answer here? What is the answer here? Well, x2 is equal to 3. This probability is given to you as 1/5 into the probability x3 is equal to 2 given x2 is equal to 3. x3 is equal यानी टाइम 3 के ऊपर आप स्टेट 2 में चले जाएं, टाइम 2 के ऊपर आप स्टेट 3 में थे. So can you go from state 3 to state 2? No, you cannot go there in one go. So this is 0. This is 0. This would not be possible. This would not be possible. Now, you might have noticed कि हमने यहाँ जितनी भी transitionary probabilities निकाली हैं. So all of these, ये x3 is equal to 1 given x2 is equal to 3. So x4 given x3, x5 given x4. सिर्फ एक पीछे वाले को देखा है, सिर्फ एक पीछे वाले को देखा है. यहाँ पे हमने जंप नहीं लगाई कि टाइम 2 के ऊपर कुछ और स्टेट है और टाइम 7 के ऊपर कुछ और स्टेट है. स्टेट टाइम 2 से टाइम 7 तक जाने के लिए मेरे पास सीधा रास्ता नहीं है कोई. I can only transition this probability transition matrix that we have talked about. This only tells you कि आज wherever you are standing, where will you be tomorrow? It does not tell you where will you be 10 days from today. It does not tell you where will you be 10 days from today. But if this matrix can tell you, कि given today, I can tell you where you are tomorrow. If I can tell you where you are tomorrow, then given that, I should be able to tell you where you are 2 days from today. And given that, I should be able to tell you where you are 3 days from today. तो अगर मैं आपको आज के बारे में बता दूं कि आज आप किधर हैं, तो कल का बता सकती है ये मैट्रिक्स, कल का डायरेक्टली बता सकती है. भाई अगर कल का पता चल गया तो फिर इसी को यूज करके परसों का भी बता दें, उसको यूज करके परसों से नेक्स्ट डे का भी बता दें. फिर इसी प्रोबेबिलिटी मैट्रिक्स, क्योंकि ये एक एक गैप के ऊपर बताती है, एक एक डे के गैप के ऊपर बता रही है आपको. यू मूव फ्रॉम n is equal to 3 to n is equal to 4, you use this probability transition matrix. Moving from 7 to 8, you use this probability transition matrix. So how can I answer a question like this? How can I answer a question like this? Okay, what is the probability that x9 is equal to 3 given x2 is equal to 2? How can I find this probability? This is called n-state transitions. N-state transitions. Okay, and we can find the or n-step transitions. I'm sorry about that. N-step transitions. Okay, and we can find this probability fairly easily. It's not too difficult. It's not too difficult. ये इसी probability matrix से पता चल सकता है. कैसे मालूम कर सकते हैं? We will talk about that next. We'll talk about that next. So first I'm going to talk about state probability distribution. State probability distribution. Okay. So for that, I am going to use this example that we had considered before. ये हमारे पास ये state 1 है, state 2 है, state 1 से 2 में जाने की probability है 1/2, which is p12. 1 से 1 में रहने की probability, which is p11, is also 1/2. p22 is equal to 1/3 and p21 is equal to 2/3. Okay. So my question is the following. Intuitive question. I would like to hear an answer. Intuitive question is this. Where do you expect? अब ये देखें, जैसे जैसे टाइम गुजरता जा रहा है हम मूव होते जा रहे हैं. कभी 1 में हैं, कभी 2 में हैं, फिर 2 में खड़े रहे, फिर 1 में आ गए, फिर 1 में खड़े रहे, फिर 1 में खड़े रहे, फिर 2 में चले गए. So you are moving between these two states. Your random process is just jumping between these two states. कभी वो उसी जगह पे रहता है, कभी वो दूसरी स्टेट में चला जाता है. Where do you expect xn most? वो ज्यादा कहां पे रहेगा? और in other words, in which state, 1 or 2, in which state do you expect to spend more time? किस स्टेट में ज्यादा टाइम स्पेंड करेंगे? आंसर करें, स्टेट 1 और स्टेट 2? स्टेट 1 एंड व्हाई? राफे, जुनेद, व्हाई? Anyone can answer? Answer is correct. You would expect कि स्टेट 1 में जो है ना relatively ज्यादा टाइम स्पेंड हो रहा है और स्टेट 2 में relatively कम टाइम स्पेंड हो रहा है. Why is that? Because the probability of remaining in the same state is higher for one, has more probability. That is correct. That is correct. The intuition is absolutely correct. And intuition makes more sense when it is shown mathematically. What is our probability transition matrix? If anyone recall, ये इसी diagram से, state transition diagram से हम probability transition matrix बना देते हैं. 1/2, 1/2, 2/3, and then 1/3. This is your probability transition matrix P. So let P x1 x1. Okay. Let P x1 x1. इसको हम क्या देते हैं? pi 1. इसको हम क्या देते हैं? pi 1. This is probability that x1 is equal to 1. Probability x1 is equal to 2. ये आपके पास 1 row 2 column वाली matrix है. 1 row 2 column वाली matrix है. So let's say this is equal to 1/2, 1/2. So that means कि आपने start किया, process अभी start किया, there is 50-50 chance. There is 50-50 chance you start with state 1 and 50-50 chance you start with state 2. ठीक है? You started with a 50-50 chance. पहले हमने कोई advantage नहीं दिया. पहले हमने कोई advantage नहीं दिया किसी state को. But people are saying कि I would expect this guy, this probability transition matrix and this Markov chain to spend more time in state 1. And I agree with that. हमने start में उसको advantage नहीं देना. Start हमने 50-50 से किया. Start हमने 50-50 से किया. What is probability of x2 taking certain value x2? So calculate करते हैं. Probability x2 is equal to 1. This would be equal to law of total probability. Probability of x2 is equal to 1 given x1 is equal to 1 into probability x1 is equal to 1 plus probability x2 is equal to 1. Oops. x2 is equal to 1 given x1 is equal to 2 into probability x1 is equal to 2. Everyone agrees with this? This is law of total probability. Law of total probability. So यहाँ पे हम values लिख देते हैं. So this is simply P21. x2 is equal to 1 given x1 is equal to 1. This is P12. I apologize. This is P11 into probability x1 is equal to 1 plus P21 into 1/2. So this is equal to what is P11? So this is 1/2 into 1/2 plus P21. P21 is 2/3 into 1/2, which is equal to आपके पास आ जाते हैं 7/12. 7/12. So the probability that x2 is equal to 2, x2 जो है, which is the time instant 2 के ऊपर state 1 हो या 2 हो, इसके अलावा और कुछ नहीं हो सकता. So this is 1 minus 7/12, which is 5/12. This is 5/12. Yeah. So देखें, we started with equal probability. We started with equal probability to be in either of the states. ठीक है? लेकिन ये पहले ही जो है ना x2 इज इक्वल टू 1 कि आप स्टेट 1 में होने की ज्यादा चांस आ गया और स्टेट 2 में होने का जरा कम चांस आ गया, सिर्फ एक ही स्टेप के अंदर, सिर्फ एक ही स्टेप के अंदर। 2 स्टेप में कितना होगा, 3 में कितना होगा, 4 में कितना होगा, ठीक है। सो आई एम गोइंग टू say this: if x1 has a distribution A, which is this vector, which is this vector, या 1:2 की मैट्रिक्स है, ठीक है, start vector या initial probability at start. If x1 is distributed as A, then x2 जो है इसकी क्या डिस्ट्रीब्यूशन होगी, A times P. वो कैसे आई है, ये हमने यहां पर लिखी हुई है, this is A times P, and you can verify this. How do you verify this? This is basically, you started with 1/2, and then you have this probability transition matrix, which is 1/2, and then 2/3 into 1/3. So this guy multiplied with this guy. So first you take this guy, multiply with this guy, and then this guy multiplied with this guy, and add them together. Okay? So matrix multiplication यहाँ पे हो रही है. So 1/2 into 1/2 plus 1/2 into 2/3, which is exactly the same here. So this will give you 7/12, 5/12. What about x3? x3 would be equal to 7/12, 5/12. Once again, 1/2, 2/3, 1/3. ये जो भी आपके पास आएगा. Now the question is, can we find an A such that A times P is equal to A? A times P is equal to A. यानी एक ऐसी चीज आपने फाइंड आउट करनी है जिसको प्रोबेबिलिटी ट्रांजिशन मैट्रिक्स से मल्टीप्लाई करें तो वही आंसर आ जाए. तो जो यहां पर आ रहा है वो यहां पर आ जाए. उसका मतलब क्या होगा, कि द प्रोबेबिलिटी ऑफ बीइंग फाउंड इन अ गिवन स्टेट will remain the same. That means you have become stationary, and this distribution A, which results in this, is called stationary distribution. You start from this stationary distribution, you will always stay in that stationary distribution. Okay. So इस particular question के लिए let me give you this 4/7, 3/7. If you multiply that with 1/2, 1/2, 2/3, ये मुझे पता नहीं है ये मैजिक नंबर कहां से आ गए 4/7, 3/7, but we will find out कि ये मैजिक नंबर कहां से आए. And 1/3, this turns out to be equal to 4/7, 3/7. aha, इसका मतलब है कि if you started off with probability of being in state 1 to be 4/7 and in state 2 with 3/7, तो एक टाइम गुजरने के बाद भी आपके पास यही आएगा. 2 टाइम गुजरने के बाद क्या होगा, सेम. 3 times, same. If you stay there for 100 time units, your probability is going to remain the same. The probability that you are in state 1 is 4/7. Probability you are in state 2 is 3/7. And this is the steady state probability of being in state 1, steady state probability of being in state 2. And you can see that इनके दरमियान में रेशो क्या है, 4:3 का रेशो. So लोगों ने जो गेस किया था पहले कि the probability that you will be in state 1, the more time you will spend in state 1, it is higher probability that you will stay in state 1. You will be spending more time in state 1. कितना was more time? 4:3 का रेशो होगा. 4:3 का रेशो होगा. And this distribution is called stationary distribution. Stationary distribution. So since I talked about the stationary distribution, I will give you the definition of stationary Markov chain. Stationary Markov chain. A Markov chain is stationary if ये दो चीजें satisfy होनी चाहिए. It has a stationary P, stationary probability transition matrix. Okay? The elements do not change, non-change, which is almost always the case, non-changing elements. Markov property hogi, so this will be the case. Okay? And then it starts with a stationary distribution. Starts with a stationary distribution. ये Markov chain आपके पास stationary होगी. So the question is, what if you don't start with a stationary distribution? What if you start with an arbitrary distribution? What if you start with an arbitrary distribution? Okay. अगर किसी arbitrary distribution से start करें, eventually in regular cases, कुछ इसके corner cases हैं, and we will talk about those corner cases. Eventually in regular cases, and those cases are for regular Markov chains. Those Markov chains are called regular Markov chains. अभी उसकी definition बाद में आएगी. But eventually you will end up in stationary distribution. What that means is that you start with alpha 1 minus alpha. You are in state 1 with probability alpha and state 2 with probability 1 minus alpha किसी एक time के ऊपर. And then you multiply it with 1 over 2, 2 by 3, 1 by 3. ये एक दफा अगर आपने multiply किया तो next state आ गई. फिर एक और दफा multiply करें, एक next और आ जाएगी. फिर 3 times फिर एक और state आ जाएगी. फिर 4 times एक और, 5 times एक और, 6 times एक और, and so on and so forth until you do it for a large number of times. इस matrix की power आपने लेनी है. So matrix multiplication होगी basically ये. So this matrix multiplied by with itself कितनी दफा? N number of times, where n tends to infinity. So you will end up, इसको अगर करके देखें, MATLAB पे जरा करके देखें, large n के लिए you will end up getting what we call 4 by 7, 3 by 7, 4 by 7, 3 by 7. इसको large n पे अगर कर दें तो ये आपके पास आंसर आ जाएगा. Now, if you start with an arbitrary distribution and you do it enough number of times, इसके बाद क्या होगा? Probability x infinity is equal to 1 is alpha times 4 by 7, 1 minus alpha times 4 by 7. So this would be equal to alpha times 4 by 7 plus 1 minus alpha times 4 by 7. ये आपके पास क्या आ जाएगा? This is 4 by 7. And the probability x infinity is equal to 2 is equal to 3 by 7. ये देखेंगे आपके पास stationary distribution ही आ गई. This is the same as the stationary distribution. और इसके बाद क्या होगा? इसके बाद then every time you multiply 4 by 7, 3 by 7 को 4 by 7, 3 by 7 को जब भी मैं probability transition matrix से multiply करूंगा, I will get the same guy. फिर infinity से आगे जितने मर्जी काउंट करते जाएं वो आपके पास सेम ही आंसर आएगा. What I have not answered is कि एक तो हमें ये नहीं पता चल रहा कि ये इसको इतनी दफा इस पावर पे रेज करेंगे, ये कैसे करेंगे प्रैक्टिकली. एक तो हमें ये नहीं पता चल रहा. ठीक है. दूसरे हमें ये नहीं पता चल रहा कि ये 4/7 और 3/7 ये हमने किस तरह कैलकुलेट किए, ये हमने किस तरह से कैलकुलेट किए थे. We will answer both of these questions. Okay, we'll answer both of these questions. Before that, I'm going to talk about a stationary distribution that we have already talked about. Stationary distribution of initial state. Stationary distribution of initial state. So you start with a state. You start with a state which is a stationary state. Start with this. Start with this state. Start with this state. When I say start with this state, means you have a certain probability of being in state 1, certain probability of being in state 2. You start with that probability, you will remain in this. Why 4/7, 3/7? You will remain in this state. You will remain in this state, even in a single step. Even in a single step. So एक स्टेप में अगर वहीं पे खड़े रहे तो इसका मतलब है अगले स्टेप में भी वहीं खड़े रहेंगे, and all the way up to infinity. Okay. So this is called the stationary distribution. So there is another definition which is called limiting distribution. Limiting distribution. Okay. Start in any distribution. यहाँ पे start in any distribution, not in the stationary distribution. यहाँ तो हमने कहा था ना कि stationary से start करें और stationary में खड़े रहेंगे. यहाँ पे हम कह रहे हैं start in any distribution. Start in any distribution. Stay in the Markov chain. Stay in the Markov chain long enough. Long enough. Which means कि n going to infinity. Long enough. You will reach limiting distribution. ऊपर वाली एग्जांपल में लिमिटिंग डिस्ट्रीब्यूशन इज द सेम एज स्टेशनरी डिस्ट्रीब्यूशन. तो हम उसको बार बार जो है वो करते जाएंगे तो हमारे पास आंसर जो है वो will become closer and closer to 4/7, 3/7. So how do we find the stationary distribution? How to find the stationary distribution? How to find the stationary distribution or limiting distribution? Limiting distribution तो हमने कहा बार बार उस मैट्रिक्स से मल्टीप्लाई करते जाएं. Stationary distribution कैसे फाइंड करेंगे? Well, in order to find the stationary distribution, I need pi times p is equal to pi. Okay. ये एक आपके पास वेक्टर है and p is a matrix. Okay. So pi is like this. यहाँ आपके पास वेक्टर के एलिमेंट्स हैं and then you have and then you end up getting. So this is 1:3 की मैट्रिक्स है. इसको आप जब मल्टीप्लाई करते हैं 3:3 की मैट्रिक्स के साथ you end up getting a 1:3 वाला एक वेक्टर. Okay. So what I want is कि I need a pi जिसको p से मल्टीप्लाई करें तो आपके पास सेम पाई आ जाए. How do I do that? Well, I take the transpose of this. Transpose लेते हैं इसका transpose लेते हैं. So p transpose pi transpose is equal to pi transpose. ट्रांसपोज लेने का क्या मतलब है? ट्रांसपोज लेने का मतलब रोज को कॉलम बना दें, कॉलम्स को रोज बना देंगे. ठीक है. सो ये आपके पास अगर p है, सो दिस विल बी p ट्रांसपोज मल्टीप्लाइड बाय दिस वेक्टर टिक 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 इज इक्वल टू दिस गाय टिक टिक एंड टिक. एंड यू कैन सी दैट p की जो डायमेंशंस हैं उसका ट्रांसपोज भी अगर लेंगे तो ये 3/3 रहेंगी और इसकी जो डायमेंशंस हैं वो 3/1 आ जाएंगी. एंड द resulting product here would have a dimension of 3/1. 3/1 की इसकी dimensions. 3/1 की dimension. Now इसका ट्रांसपोज लेने से हमें फायदा क्या हुआ? ट्रांसपोज लेने से हमें ये फायदा हुआ कि recall किसी को याद है कि A matrix A times this vector V is equal to lambda times V. ये इक्वेशन हमने कहीं देखी होगी, A is a matrix, A is a matrix. ये कहां पे देखी थी? When A times V is equal to lambda times V. So when you have a matrix, A and you multiply it with a vector and you get the same vector multiplied with a constant. This is what we define V as the eigenvectors. V are the eigenvectors and lambda are the eigenvalues. Lambda are the eigenvalues. जब भी किसी मैट्रिक्स को एक वेक्टर से मल्टीप्लाई करें और आपके पास वही वेक्टर आ जाए विद सम फैक्टर लैम्डा, ठीक है, देन दैट वेक्टर इज एन आइगन वेक्टर, और ये एक से ज्यादा हो सकते हैं. दैट वेक्टर वुड बी एन आइगन वेक्टर. जितने रैंक होगा आपका मैट्रिक्स का उतने आपके पास आइगन वेक्टर्स आ जाएंगे, उतनी आपके पास आइगन वैल्यूज आ जाएंगे. ठीक है. नाउ if you notice, if you compare these two guys, ठीक है, so in this case we are saying कि P ट्रांसपोज जो है उसका एक आइगन वेक्टर हमने मालूम करना है, ऐसा आइगन वेक्टर जो लैम्डा इज इक्वल टू 1 के कॉरेस्पॉन्डिंग हो. ठीक है. सो दैट मीन्स कि फाइंड एन आइगन वेक्टर ऑफ P transpose, find an eigenvector of P transpose corresponding to the eigenvalue of 1. eigenvalue of 1 के corresponding जो वेक्टर आया, वो वेक्टर जो आपके पास आया, that is your pi transpose. pi transpose पता चल गया तो pi पता चल गया. pi पता चल गया तो that is your stationary distribution. You can certainly do it. So it might sometimes happen that the limiting distribution will not exist. Example. Actually, let me call it a counter example. And this counter example shows that sometimes limiting distribution does not exist. Sometimes the limiting distribution does not exist. Okay. We may still have a stationary distribution. ताकि स्टेशनरी डिस्ट्रीब्यूशन से स्टार्ट किया तो वहीं पे फंसे रहेंगे. किसी और जगह से स्टार्ट कर दिया तो लिमिटिंग डिस्ट्रीब्यूशन एग्जिस्ट नहीं करती, तो यू विल नेवर गो टू द स्टेशनरी डिस्ट्रीब्यूशन. Now I'm going to make this definition. If a Markov chain is regular, and regular का मतलब है कि it is regular को explain करने के लिए I am going to use two more words जो हमने पहले नहीं सुने होंगे. Well, सुने होंगे but not for Markov chains, तो उनको भी explain करना पड़ेगा. If a Markov chain is regular का मतलब है it is irreducible. ठीक है. इस वर्ड का हमें मतलब नहीं पता इसका क्या मतलब है. एंड aperiodic, हमें ये भी नहीं पता कि aperiodic मार्कॉफ चेन क्या होती है. बट एक चीज पता चल गई कि अगर एक मार्कॉफ चेन रेगुलर है तो दैट मींस कि वो irreducible और पीरियोडिक होगी तो वो रेगुलर मार्कॉफ चेन होगी. दैट काइंड ऑफ अ मार्कॉफ चेन इज कॉल्ड ए रेगुलर मार्कॉफ चेन. वी विल गिव द डेफिनेशन. हम आपको बताएंगे कि irreducible क्या होती है और aperiodic क्या होती है, but not right now. Okay, I'm just going to give you the definition right now. Then the stationary distribution is the limiting distribution. is the limiting distribution. Then the stationary distribution is the limiting distribution. Okay? So in that case, limiting distribution exist करेगी और वो stationary distribution की ही होगी. Okay? But if the Markov chain is not regular, then there is no guarantee that the limiting distribution will exist. Okay? So hand-wavy definition of irreducible Markov chain. Okay. Start from any state. You can visit, if you can visit any other state with non-zero probability. अगर कहीं से रास्ता नहीं बंद हुआ हुआ, with non-zero probability in finite number of steps. So that kind of a Markov chain would be an irreducible Markov chain. Okay. What about aperiodic? Here we again informal definition. Okay. A Markov chain which does not show deterministic visiting pattern. उसका जो visiting pattern जो है वो deterministic नहीं होगा. Deterministic means periodic नहीं होगा. And we will give you an example. एक ऐसी Markov chain है कि example, ये Markov chain है आपके पास, you are in state 1 and you are in state 2. With probability 1 you go to state 1, probability 2 you go to state 2. ऐसी एक चीज हमने देखी थी, ऐसी एक चीज मिलती जुलती एक चीज हमने देखी थी, रैंडम टेलीग्राफ सिग्नल जो है वो पोलैरिटी जो है वो चेंज करता था. हाँ ये बात है कि उसमें टाइम डिस्क्रीट नहीं था. रैंडम टेलीग्राफ सिग्नल में टाइम डिस्क्रीट नहीं था, टाइम कंटिन्यूअस था, बट वो पोलैरिटी चेंज करता था हर दफा. यू वर गारंटीड कि वो जहां पे भी इवेंट अकर करेगा, वो सॉन अराइवल इवेंट अकर करेगा, वो अपनी पोलैरिटी चेंज कर देंगे. सो this is an example of a Markov chain which is periodic, and the probability transition matrix for this guy is 0, 1 and then 1, 0. This is the probability transition matrix. What is the stationary distribution? इसकी क्या होगी? इसकी stationary distribution है 1/2. सिमेट्री है तो हमें नजर आ रहा है कि it would be 1/2. Because of symmetry, I cannot give higher weight to 1 or 2. तो दोनों को 1/2 डाल देते हैं. तो करके देखते हैं 0, 1, 1, 0. So this 1/2 multiplied by 0, 1/2 multiplied by 1, you will get 1/2, and then again 1/2, and you are done. That is all we wanted to show. Okay, ये stationary distribution. So ये इसकी stationary distribution. Is there a limiting distribution? अगर होगी तो वो stationary ही होगी. Is there a limiting distribution? And the answer is no. And the reason is why? And the reason is if you start in the stationary distribution, you will have the stationary distribution. If you start in any other state, any other distribution, किसी और distribution में आपने start कर लिया, you will never ever converge to the stationary distribution. करके देख लें. You will never converge to the stationary distribution. So करके देख लें. 1/3, 2/3 से start किया, and then 0, 1, 1, 0. ठीक है. So this will give you 2/3 and then 1/3. फिर इससे multiply करके देखें. So 2/3, 1/3 से multiply करके देखें. 0, 1, 1, 0, and you will get what you will get is 1/3, 2/3. ये देखें ये वही आ गया। सो यू विल नेवर, आप इन दो के बीच में चक्कर खाते रहेंगे, दो के बीच में, दो डिस्ट्रीब्यूशंस के बीच में चक्कर खाते रहेंगे। यू विल नेवर गो टू द स्टेशनरी डिस्ट्रीब्यूशन, कभी स्टेशनरी डिस्ट्रीब्यूशन पे जाएंगे। और ये हमें लग भी रहा है, ये 1 से 2 में चले जाएंगे, 2 से 1 में, 1 से 2 में, 2 से 1 में, 1 से 2 में, 2 में, एंड सो ऑन एंड सो फोर्थ। कभी कन्वर्ज नहीं करेंगे स्टेशनरी डिस्ट्रीब्यूशन है। एंड दिस आल्सो शोज द periodic behavior, this is a periodic, it is not aperiodic अगर होती, अगर aperiodic होती और साथ में irreducible भी होती, उसकी भी एग्जांपल्स आगे आएंगी, then I would have called this a regular Markov chain, and for the regular Markov chain I would have had the stationary distribution equal to the limiting distribution. Not in this case, okay. So how do you solve this equations for stationary distribution? Okay, ये ऊपर वाली एग्जांपल दोबारा कंसीडर कर लेते हैं. Let's say you have alpha beta as the stationary distribution. Okay, 1/2, 1/2, 2/3, 1/3. Same example. I want this to be equal to alpha beta. And basically, what I'm trying to do here is I'm trying to finding the stationary distribution. एक तो तरीका आपको बताया था आइगन वेक्टर्स को, आइगन वेक्टर को यूज करें जो आइगन वैल्यू 1 के कॉरेस्पॉन्डिंग हो. So this is another method of finding the stationary distribution, and that is by definition. This is our stationary distribution. So this should be equal to 1/2 alpha plus 2/3 beta is equal to alpha, and 1/2 alpha plus 1/3 beta is equal to beta. इन दोनों इक्वेशंस को आप सॉल्व ही नहीं कर सकते. Why? Because they are the same equation. Homogeneous equation है. However, you do know that alpha plus beta is equal to 1. You also know this. Alpha plus beta is equal to 1. इसको सॉल्व करें. Alpha is equal to 1 minus beta. या इसमें पुट कर दें, which basically are the same equations. Then you will end up getting alpha is equal to 4/7, beta is equal to 3/7. ये वही है जो हमने पहले मालूम की थी, जो हमने पहले चुप करके लिख दी थी, without knowing कि ये कहां से आई है. Now we know कि ये कहां से आई है. So we will have few more examples and state transitions from one state to another state after a large number of steps. ठीक है, तो आज तो हमने probability transitions की हैं. किस तरह की कि from today what will happen tomorrow. So next time we will talk about from today what will happen 10 days from today. So we will solve some of those examples as well in the next class, and this is it, what we wanted to talk about today. कोई question है so feel free to ask, otherwise I'm going to unshare and close the session. जी
ऊपर जो आपने बताया था arbitrary distribution से अगर हम start करें, and then you said if you take large enough n, then the matrix turns to 4/7, 3/7, 4/7, 3/7. उसको जरा आप repeat कर सकते हैं?
क्या कर सकते हैं जी?
सर repeat कर सकते हैं वो किस तरह से होगा? यही exact.
हाँ. So if you take this matrix, या आप ऐसे करें, आप ये वाली मैट्रिक्स ले लें और इसके ऊपर लार्ज n, इसका मतलब है कि इसको आप मल्टीप्लाई करना शुरू कर दें यहाँ. So ये if this is matrix A, इसको मैं कहता हूँ matrix A है. This is matrix A. क्यों कहता हूँ मैं इसको? P ही कह देता हूँ, इसको मैं P कह देता हूँ. P को आप P से मल्टीप्लाई करें. So ये 2/2 की मैट्रिक्स है, उसको एक और इसी 2/2 की मैट्रिक्स से मल्टीप्लाई करें, 2 दफा करें, 3 दफा करें. If you do it infinite times, you will end up getting this. In fact, आपको थोड़े से टाइम्स करने के बाद जो है ना वो पता चल जाएगा you are getting something close to 4/7, 3/7. और फिर 4/7, 3/7 जब आपको ये मिल रहा है तो आपको बहुत ज्यादा ये पावर्स ऊपर करने से, obviously this is not a very practical way of solving it. सो उसको किसी भी स्टार्टिंग डिस्ट्रीब्यूशन से आप मल्टीप्लाई करें, you will end up with the stationary distribution. What that means is कि आपने किसी भी आर्बिट्रेरी डिस्ट्रीब्यूशन अल्फा 1 माइनस अल्फा से स्टार्ट किया और आपने लार्ज एन का मतलब है कि बहुत सारे स्टेप्स से गुजार दिया, एक दफा दो दफा, इसका मतलब है कि बहुत देर तक उस मार्कऑफ चेन को चलता रहने दिया n इज इक्वल टू 1 2 3 4 5 6 7 8 10 दफा जब आपने कर दिया, 20 दफा 100 दफा कर दिया, तो ये बहुत हर दफा जो है ना, when it goes from one state to another, एक स्टेप से दूसरे स्टेप पे जाती है, एक स्टेप से दूसरे स्टेप पे जाती है, एक पी से मल्टीप्लाई होती है उनकी probability distribution, and if you have sufficient of those p's you will end up getting this matrix. इसके साथ देखें, इस मैट्रिक्स के साथ आप अल्फा 1 माइनस अल्फा अप्लाई करें, मल्टीप्लाई करें, तो you end up getting 4/7 3/7 which is the stationary distribution. अब मैं 4/7 3/7 को वापस इसके साथ दोबारा मल्टीप्लाई करूंगा, I will always get 4/7 3/7. Does that make sense?
Yes, sir. Thank you.
Okay, great. Any other question before we close the session? Okay, I'm going to stop the share and close the session. Thank you very much for showing up in the morning. I'll upload the recording whenever it becomes available.